Today, we have two lectures. The first lecture is going to be a pair programming lecture, where I guess I'm going to do the typing, and maybe you're going to do some amount of the thinking. And the goal is to not just program, but it's to teach you how to program a little processor in BlueSpec. And it's just a way to get a little bit hands-on on the full thing, and then to think a little bit about what kind of optimization we could do, and then how we would prove them correct mathematically, and these kind of things. So I don't know how much you know about processors, but I'm assuming that you know not much. And then I'm just going to explain a lot of those things. So let's go back to the very basics. You know, there is a very good 1947 papers by John von Neumann, on the draft on the EDVAC machine. And that paper was sort of first officially to propose a store program computer. What's a store program computer? It's a program, it's a computer in which the program is data. That is, it's not a machine that could do one kind of thing. It's a machine where you can reprogram it by changing the program that is in the memory. And you know, before that, you could sort of configure machines, but it would not be universal. You could not run an arbitrary program, and program was not explicitly data. And so this idea is still there today. And I basically want to explain a little bit how easy that idea is to implement, and how very quickly you can get up and running with a processor running actual C code. And that's hopefully what we will have by the end of the lecture, by standing on the million of open source tools that are available. So we are going to build a little RISC-V processor, not completely compatible, but that supports a subset of the instruction set. Okay, so the very basics is the fact that in this, if we think back about the abstract machine that we are trying to build, a processor basically, conceptually, the architectural state is composed of three kinds of states. There is a program counter, and the program counter is just telling me where I am currently, which instruction I should be executing right now, and the instruction should stand in memory. There is a memory which should both hold the instructions and the data of your program. So the memory is uniformly handling the requests that correspond to instructions, and also the load and stores that correspond to the data that you're going to read and write when you're executing your program. And there is a bunch of registers. Typically in RISC-V there are 32 registers, and all of them are basically going to be used to hold values that you have brought back to memory, from memory, and then you're going to do little operation, typically addition, arithmetic and logical units operations, and updating the register file. And when you are you have produced some value, you're going to write back these values that you have put in registers by storing them back to memory, and that's basically the whole story of what the processor is. Okay, so in terms of states, there's really three pieces of states, and then the only question is how do you glue those pieces of states? Because here in there is no adder, no multiplier, nothing. There's just the states, and the question is how do you glue the state? Okay, so if we go top down, the machine should go through basically 4 steps to execute a program. First, it should say what we call the fetch step, in which you should look at the program counter, and you should ask the memory, please tell me what is at that memory cell location. Okay? So conceptually, this is basically saying request memory and at the cell corresponding to what is currently in the PC. Okay. Then at some point later, the memory will not respond instantaneously. It might take time to respond. So later you're going to get a response back from memory. And when you get that response, you know that the instruction that you care about. So what you should do, it's just a bit pattern of 32 bits. You should decode it to know what kind of instruction this is. Is it an add? Is it a load? Is it a store? Is it what kind of instructions? So the second step is basically doing decoding. And part of decoding is also going to say, well, if I am doing an add, I should read the values corresponding to the value I need to do the addition. So if I do register 2 plus register 3, in the instruction, I'm only going to get the index of the registers out of the 32 registers. So maybe it's going to tell me, for example, add register 2 and register 3 and put the results into register 1. And then what I should do is first, gather the value corresponding to those two registers simply by reading the register file. Then I should execute the instructions, which is actually performing the addition, performing, if it's a load instruction, I should send a load to memory. Notice that the first load I sent here was to gather an instruction, but if I send a load to main memory, it's a program load that was part of my program. So, I execute, is it an ALU instruction? Is it a control flow instruction? Is it a memory instruction? And then for almost every instruction, I could stop there, but for a load, I need to wait until my response to the load is coming back to memory before I can write the value to the register, and then change the PC to go to the next instructions. In most situations, the next instruction is just PC plus 1, actually PC plus 4, because instructions are 32 bits and addresses are bytes. So you have little, the two bottom bits are always zeros in the addresses for an instruction. And then we start, rinse and repeat, okay? And if it's a control flow instruction, then I should update the control, where I should say, actually, PC, it's a little bit of a fork here. I should go off somewhere else, which was specified by the instructions. Is that very clear to everyone? Okay, so we basically know that we have 4 steps that we want to do, and so the first step is called write back, typically. So we will have to write 4 rules. So I already wrote a little bit of code here. Actually, let me tell you one thing about the piece of code that I wrote. So I told you about the state of the machine, but I didn't tell you how the world interfaces with that machine. And how do you tell the processor to do something? And how does the processor tell you that it did something? And if you assume we are back in 1980s, a very good model to think of that is basically saying there is one way to interact back and forth, and it's if you send a load or a store to a special location, it's actually not memory. It's a sort of fake memory, so we call that memory mapped IO. And if I send a load to that special address, then actually what it does, it's basically looking, is it the case that someone has pushed a key on their keyboard and I should look at the value corresponding to that key? And if it's a store, I basically send that as a character to print on the screen, okay? So I can basically think that the interface between my processor and the outside world is just 2 methods. One is put char and one is get char, okay? And to make things simpler, we are even just gonna say that it's a machine where there's just outputs from it. This way it's very simple. We can just print ASCII out and then that's good enough. Okay, so we have already identified a little bit what are the piece of states. So let's write them in BlueSpec. So we can declare that we have a register which holds a 32-bit value and we call it the PC. And then we need to say, what is the submodule of that register? Well, the submodule of that register is the make-reg submodule. And for the memory, so here I am assuming that I've basically written, or someone had given to me the primitive register and the primitive memory, okay? I could have written them. I could also, later, I could replace make memory by make cached memory, in which I have a refinement that I've proven that my cached memory is actually equivalent to my memory here. And by the refinement theorem, everything should be preserved. Okay, so I said there is a PC, and then there's a register file. So a register file is basically just a bunch of registers. So there is a construct to be able to just say an array of register. And here, so you can already wonder a little bit what the type system of that beast. And it's fairly, actually it's fairly sophisticated. So you can already notice that there are modules which are parameterized polymorphically by the type of the thing that they are holding. Now you know a little bit about polymorphism. And here you see that the types are themselves depending on values. So, is it dependent types? No, it's actually not dependent types, it's type level integers. So this 32 here is not a value, it's a type level integer value. So it's different from the 32 that lives in the world of value, which if you're familiar with a little bit of this kind of type system feature, I thought I would mention. Okay, so we have our 3 pieces of states. Okay, very good. And now we want to be able to start writing our first row, and our first row is going to be fetch. Oh, we need one more thing. we need to remember in which of the states we are currently in. Are we in the state to fetch, the state to decode, the state to execute? Otherwise, if I write one rule per cases of state machine, but I don't remember in the case in which I am, then all those rules are going to fire concurrently, and who knows what I'm going to do? I need to do them sequentially. So I need to create a little enumeration type, which basically say, well, I don't have to do enumeration, but I can do enumeration, which describes the different case that I can be in. And so I can be in fetch, I can be in decode, I can be in execute, and I can be in write back. Okay? And I call that the state of the processor. And there is type classes in BlueSpec. Let's not worry too much about it. So here I just derived, I declared the new types, and I say, and by the way, this type, you should give it two functions automatically that you can derive, a notion of equality on that type, which is fairly easy to define. You just derive it by automatically saying that it's equal if it's the same constructor and not equal otherwise. And then I want to be able to represent this as bit pattern, because registers need to be able to represent things as bit pattern. So it needs to be encoded on a finite number of bits, which not every type can be. So you need to do that. Yes?
So you need to be able to represent it as bits.
Sorry, what do you say?
You need to represent it as bits.
So
is it going to be some ghost state, and then it's going to be not in the module, or is it going to be more?
So to be able to write, to be able to hold, let me write it here. So I'm going to have a new piece of state here, which is going to hold a state processor. And here I'm going to say it's called the current state, and I'm going to say I start in state fetch. To be able to write that line, the compiler says the only way in which I could build a register is that the type of thing you're trying to hold in the register must be finitely representable. Otherwise, I could not make hardware for it. If I had a list here that I declared, then the compiler would tell me, no, but you can't put a list in a register because it's unbounded and a register has finite length. So this bit deriving is just a way for the compiler to know that it's finitely represented. And internally, so we are never going to actually use it. It's always going to be implicit. But the compiler knows that every time you try to write to the register, it will basically convert it to a bit pattern, put it in the register, and then convert it back to the enumeration type. And this doesn't cost any hardware. It's just basically representation for the top-level user. Does it make sense?
Yes.
OK. So now we have our new little enumeration. And basically, we want to say, well, we only fetch if we are in the fetch states, right? So current state equal fetch. OK. And what should we do when we fetch? It's very easy. We have just described it. We need to, yes, we need to ask the memory what is at the PC currently. So how do we do that? Well, we just create the, so we need to create a struct that corresponds to the request. So instead of doing it in line, I prefer to first define the request here. So the type of request, the type of memories that I'm using here is called a BRAM. Doesn't really matter. It's a technical detail. But basically, it has 3 fields. You need to say, do I send a read or a write? So here it's a read, so write is false. Then I need to say, what is the address to which I'm expressing my request? And then I need to say, what is the data in case where it is a write? OK? And then there is a last field, which is, what is, if it were a write, do you want to get a response on that write or not? And let's say that here it's not a write, so it should not matter, but let's just be preemptively safe and just specify this thing. So what is the address at which I should write? Well, so here there is a little bit of a trick, and that's a standard problem of dealing with hardware, is the fact that you always have different addressing scheme in the machine. So the PC is holding a 32-bit value, which is a byte address PC. But at the same time, my memory, I described that it's a set of 2 to the 16 cells, and that they are all holding a 32-bit value. So if my PC is a byte address, and I want to know where am I trying to read a byte-aligned, a word-aligned word in that memory, I will need to shift my address by 2 on the right to know what is the word address in my memory instead of the byte address in my memory. Does that make sense to everyone? Okay, so I will just have to say, well, I need to take my PC and I need to shift it by 2 on the right. And then what I get is not of the right type, because what I get is going to be, again, a 32-bit number, but it's expecting a 16-bit address, so I will need to truncate the upper bit. Okay? And here, because it's a read request, then I don't need to put the data, so I could put the question mark, which is an undefined value. Okay? So here I crafted my little value for the request I want to send, and then I just send it by calling the method that corresponds to sending this thing. So I slightly lied to you yesterday, but not much, so it's okay. What I lied is that actually, for programmability reasons, sometimes you don't want all the methods of a module to be flat. You want to organize it in a hierarchy, in a namespace. So here, we could have, if we were in the formalism of yesterday, we would just have had mem.put. But it happens that memory sometimes has multiple ports. You send multiple outstanding requests on different ports. And so you basically have 2 different subinterface, port A and port B. And then you have a subinterface for request and subinterface for response. So it doesn't really matter this sort of namespacing qualification. You can think of it like this. Fundamentally, it's as if I had just removed all those things, just a convenience feature. And so here, when I did that, I'm basically guaranteeing that if I ever send a thing, then it must be the case that I'm in the fetch state. And I will send the expected request. And then I need to do one more thing. What I need to do last? Yes?
I assume to actually take the value and sort somewhere.
So we don't have yet, we cannot, so good remark, but we can't do that because we just send the request to main memory, but we cannot in the same rule get the response because precisely it's going to take one step inside the memory before you can ever get the response. So we have no hope of getting the response in fetch. We will only get the response in decode. So that's not what's missing. Yes? Exactly. No, we need to go to decode. Okay? So very easy. We say current state. And so here, if I wanted to be very precise, actually you should have already complained. This doesn't make any sense in what we said yesterday. That's what I should be doing, and that I should be doing this as well. And then I should set it to decode. But it happened to be the case that there is syntax sugar in BlueSpec. There is actually a lot of, oh, actually, I think the author of BlueSpec doesn't like to call it syntax sugar. He likes to call it syntax spices. Nickel. And there is syntax spice for this. And if I don't mention anything, it's basically automatically calling the read method if there is a read method. Okay? Because it's too annoying. There's so many registers that you don't want to call the method. Okay, very good. So what should we do next? So next we should write a decode rule. And it will surprise nobody that I write this thing. What should we do in decode? Yes, we should get the response. So how do we get the response? Well, so I told you in the formalism I told you yesterday, there are action methods to DQ and there is value method to read the value. This pattern is so common that you have a pair of twin methods that in BlueSpec there is support to patch 2 of them in one call. And that's called an action value, which is basically it returns the value and does the action associated to it. And the notation to do that is just an arrow instead of an equal. And if so there is a method called mem.porta.response.get. And what this thing does is basically, it's both conceptually calling a DQ method and calling a first method and binding the first value to inster. Yes?
Is it guaranteed that the response will be ready? Because I would have expected that in the condition for decode, we would add something like, well,
yes.
The memory response is
Yes. And that's where BlueSpec is really helpful. And that's why BlueSpec is, so what the question was is, well, I am surprised that you don't need to check somewhere that the response is available and something like this. And the full rationale of BlueSpec is to say, well, if I have this view of method call, I should be able to derive the control signal automatically in the compiler. And that's exactly what the compiler does. That is, every time you have a method, the compiler ensures that either the full method happened or nothing happened, or a rule, either the full thing happened or nothing happened. And it's gonna lift all the ready signal of the sub-methods, which I briefly explained yesterday, as an end of all the possible things that can happen. And so I don't need to do that. Basically, I have the guarantee that if that condition is true and all the conditions that are necessary for the methods to be true are true, then the thing will happen. Otherwise, it won't happen. Okay? So that's one of the great, one of the things that make it much easier to write BlueSpec programs than standard RTL, like Verilog or something like this, is because you can't get the control wrong, because you don't write the control. It's the compiler that writes the control signals and all those ready and stuff. Okay, so I get back the instructions. So now that's the part that becomes very painful because I need to decode that instructions. But thankfully, this is actually boilerplate. There is a document which is about 200 pages long that explains how to decode and execute instructions. And once in your life, when you start your PhD, you write a long file. Yeah, maybe there's a copyright. Yes, there's a copyright. Okay. You basically say, okay, how do I create all the internal representations of an instructions from 32 bits? And then, you know, you have, okay, so I want to construct this struct. Then you have to copy paste all the different opcodes from the documentation, and you don't want to get them wrong, so you generate them automatically. Then you need to say, when is it the case that it's a legal instruction, blah, 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 blah. And it's about like 300 lines, but I think we never touched it since 2018, so that's a one-time thing you need to do. And part of this is basically, so decoding the instruction, but similarly to decoding an instructions, you also have the same thing on executing, which is once you have decoded an instructions, what does it mean to execute some kind of instruction is also completely specified. It's boring. This is not part of the computer architecture. This is part of the spec of what bit pattern correspond to what, and then what should you do in which case. So here, for example, once we have decoded, then what should be the output of the ALU is like, well, you know, fairly straightforward. If you have asked for an add or a subtraction, then you should do an add or a subtraction. If you want to do a shift logical left, then you should do a shift logical left. If you want to do set less than, you should do a set less than, and so on and so forth. Okay? So this is basically sort of the specification of RISC-V in terms of combinational logic. But it's fairly disjoint from the architecture of the machine, which is this sequence of things, which most of computer architecture doesn't care much about changing these parts, but matter much about optimizing that state machine, which is going to be really silly, and we can do much better than this sort of four-stage machine, as I'm going to explain a little bit later. Okay, so thankfully, I have written, actually, I don't even know if that version is I have written. I think it might be Andy. We have available a bunch of functions, and one of them is basically a function to decode. And so we can say, well, you know, I want to apply the pure function of decoding the instructions. And on the right-hand side, I did this morning the live coding, so I have the cheat code. It took about 30 minutes, so I thought by factor 3 I should be good. So decode inst. Oh, there's auto-completion. Whoa, cool. And then I want to decode the instruction. Oops. Okay. And then I want to read all the values in the registers. And then I should put them somewhere, right? Because I will need them. So one important thing here is first that in that stage, I just got back the instruction from main memory. But I will still need the instruction on every single other stage of my thing, right? And if I don't store it somewhere, I'm going to lose it, right? Currently it's there, but I didn't put it in a state. So if I don't do anything after I execute that decode instruction, I will not have the decoded instruction anymore. And if I want it back, I should send another load to main memory. And that's not what I want. So I want to shelve it to be able to keep using this inster both in execute and write back. So I need one more piece of states. I need to say, okay, I want to store that instructions. Hop. So let's call that the microarchitectural state. And so we need to basically remember that instructions, and we want to keep it as if it were decoded. And so we will call that the dinst register. And at the beginning of time, it doesn't really matter what there is. I don't know what happened. Okay. And now, when you have this instruction here, you can store it by putting it, into dinst. Okay. Okay. And then I want to be able to read the registers that I care about. Because I will need them to be able to do this in the execute stage. So same thing, I need to basically have the source register. So in RISC-V, there is this nice structural property that every instructions touch at most 2 sources and produce 1 destination, at most 1 destination. So I know that I will somehow need sort of microarchitectural states to store, to store the source, number 1. And I will need another one to sort the source number 2. And I will need another one to store the destination, or the produced value. And now I want to be able to access the register file and write RS1 and RS2. So that's very easy. So because I have already written a function which allows me to access which index it is from the decoded instruction, and that's just this is all combinational stuff. So it's a pure functions where if I apply the guessed int field to a decoded instruction, not actually to the direct bit pattern, that's an interesting one, then I can just access it like this, up and up. Okay. And if I want to be able to read the register file, it's also very easy. I just can read the register file by accessing it to the index, and then same thing to the index. So this is syntactic spice. Again, why is it syntactic spice? Well, it's accessing the read method of this RS1 ID index elements. Concretely what it is doing is that this dot read again, okay? Actually, there is a weird, it's not a weird thing, but it's very common in most computer architecture. Very often, it's in most ISA, it's important to have one register that always holds 0. You never want to do anything with it but 0, and in RISC-V, the 0th register. So a typical thing that you do is either you make sure you never write to the 0 register, or you just hardcode something where you say, well, you know, if the RS1 is equal to 0, then you should just return 0. Otherwise, you should return the value that is held there. And that's kind of like a waste because I created 32 registers. And I actually never need the first one. But to avoid off by 1 errors, I prefer to afford an extra registers. Okay. Okay. And then I want to basically write, so I guess I could write it, everything there to make it cleaner. So I need to write RS1. So here I'm going to have a problem. So let's, I will have a shadowing problem. So let's, let's rename them. So here, notice that on the right-hand side, this is not a case where I'm doing a read method call. This is referring to a variable, okay? And then this is boring. We just do the same thing with RS2. And if I make a mistake, you catch me. And then what should we do next? We should go to execute, okay? Okay, so this is very easy, right? We really have not done anything, okay? So now we need to do execute.
I think, so for RS2 equals RS1 index equals 0?
Aha, you found a bug. That's what you're saying. Yes, I agree. Thank you. How many hours do you think it would have taken us to debug that bug? The answer is too many. Okay, so you're starting the pattern, right? So what should we do here? So that's a difficult one. It's a difficult one because now we need to do the thing. We need to know, is it a ALU instruction, in which case I need to call the semantics of RISC-V that tells me what is the new value? Is it a load instruction, in which case I should send something to memory? Is it a store instruction, in which case I should also send something to memory? Or is it a control flow instruction, which is a jump or a branch or something like this, in which case I should change the PC, okay? So there will be a few cases. It's going to be most of the times at probably the next 15 minutes, but then we are almost done and we can run C programs. One last thing, we need to not forget a special case where if it's a load or a store to a special address, we need to say, actually, this is not memory. This is to print on the screen or to do something with the outside wall. Okay, everyone on board? So let's go. So first, the key function that we are going to call is going to be the function that produce the RISC-V semantics for an instructions. And this is basically simply requiring to, so if you read the spec, if you read the type of the function, you will realize that the new value is depending on a bunch of things. It's depending on the value of the two sources. It's depending on the instructions that you're trying to execute. And it's depending on something called the immediate field, which is something that itself depends on the instruction. But for some reason, we had split it into parts. So then we need to do one level of indirection in which we basically say hop. And we don't need to know the details of what is happening in those functions. We can consider them completely abstract as far as we are concerned. Okay? Then if we ever have to do a load or a store, the address is specified to actually be what was in RV1 plus immediate. Okay. And then we can start doing our actual work. So we need to say, well, is it a memory instruction? And then if it's a memory instruction, we will have to do some stuff. Or is it not a memory instruction, in which case we will have to do more stuff. And in case where it's, in both cases, we will have to do things in common. So we will put them below. And the thing that we will have to do in common, at least, is to go to the next state, right? So that we can put here. Okay? Okay. So now we need to do, memory instruction is probably not correct. Yes. Okay. So what happens for the memory instructions? So for the memory instructions, we need to know, is it a load or a store? Because that's going to create different kind of requests to main memory. And then we have basically all we need because, we have computed the address, we have computed the data that we want to send. So it should be fairly straightforward. Actually, there is one thing that we are not going to do. That might be important for the demo in about 15 minutes, is the fact that we are not going to handle, so in RISC-V there are load words, which are load aligned, but there is also load bytes. If you just want to read one byte, and you need to worry about the offset within the word when you do load byte. And this was adding an extra 10 line of code that I thought would just make everything more complicated. So we are not supporting byte instructions in RISC-V right now, but let's assume that this will be okay. Okay, so how do we do that? How do we handle the load instructions? That's fairly easy. So in case of store instruction, data to store, actually we can overwrite data because there is this nice feature in BlueSpec that variables that are local can be sort of locally overwritten, shadowed in the way that you would expect. And in this case, it's known that it's RV2. So this is just, again, reading the specification. And then if you just look at the type of memory instruction, same thing. You need to look at the bit 5 of the instruction. Okay, very good. I'm happy. Hop. And if it's 1, it means that it's a store. Otherwise, it means that it's a load. And then we need to do the same thing. We actually copy-paste our code. We need to create a request. Hop. For the memory. Hop. And then when is it a store? It's when that is true. And then we will just say, do we want a response on store? So here we need to be careful, because if we say, do I want to create an artificial bug? Maybe I do want to create an artificial bug. Okay, so let's not talk about that and we will run into the wall. So we just want to say, what is the address at which we want to write? Well, the spec told us that it was the address. And what is the data at which we want to write? Well, actually that's the same thing as before. It's a truncate, same business, because the address is in byte and we have this thing in words, and then the data is data. Okay? And now, when do we want to send this request? Well, we want to send this request if and only if the address is not one of the address to the outside world. Okay? And so if it's an MMIO address, which is why there was a function at the top of the thing, then what do we want to do? We want to actually do the effect of the outside world. So that's going to be the only side effect we will have in our program. So I decided to have just 2 addresses. One is picked sort of semi-randomly. I just picked F000, FFF0. And that's an address to which I decided that this was a put char thing. So if you do anything to that address, we are just going to consider that this is printing on the screen. So we are going to do an F writes on std out of just a character, which is the data that we have. And we just print the bottom byte of the data. Okay, yes?
Is this F-write like a virtual function that interacts with simulation?
Yeah, so we are going to see that. That's a very good question. And here I'm basically using the fact that BlueSpec is a pragmatic language. So for a long time it was, I mean, it's still an industrial language, right? The compiler is about 500,000 lines of code. People have written very significant things in it. So you need a lot of way out of the jail of pure things. And one of the things that is very convenient is to be able to debug, to be able to display things in arbitrary places. It happened to be the case that Verilog already has this support, so there is a nice way in which you can translate to Verilog and basically have side effects of the form opening a file, printing, writing, and stuff like this. But keep in mind your question about simulation business because it's going to be relevant soon. Okay? And then we have another address, which is how do we stop this hell of a machine? If we write to a special address, let's say, hop, if address is equal to, I think it's all f, f, then we just stop the world. And what I did is just, I display terminate. Okay? We actually don't need to put the begin end if we have a single thing. So let's be up a little bit, saving time and space. Okay, very good. And in the case where it is not an MMI address, then that's when we need to send the request to main memory. I don't understand why the things is always breaking indentation, whatever. Then we said mem.sporta.request.put, and then we put the request. Does it make sense? Yes, question. You are saying there is a bug in my code, and that's correct. Thank you. How do I terminate? There is a primitive in Verilog that says stop the simulation. Okay? And how would you actually do it in real hardware if you are on FPGA? So you would actually not do a display statement or an F-write statement. What you would have is that you would have a queue, and that queue would interface with the outside world, and you would have basically two queues, one queue for the characters, and one queue for the signal stop the machine. And externally, you would have something that basically, if you receive anything that tells you to stop the machine, you just power off the machines. Okay? But I thought I would avoid this level of indirection for this little demonstration. Okay, so there is a typo here that I see. Very good. And what else should we do? We should send this request. We are good. And then we need to get out of this case of memory instructions. So now we need to do only the case for control instructions. We have already handled the common case. Oh, some things that nobody asked about, but it's like kind of interesting, is that I very early in my function, in my role, I put the exact ALU function, and not every not every instructions require me to actually execute, the function. Like if it's not an ALU instruction, why am I always calling that? Someone has a clue why I put that here? It seems that this is very inefficient, right? I'm always saying do the work, even though it becomes irrelevant because I don't use it. Yes? Okay, why does it not matter? It doesn't matter for semantics, yeah? But could it matter for performance somehow? Yes?
Well, I assume all of the relevant parts of data that are independent are executed simultaneously.
Yes, exactly. Hardware is fundamentally parallel, right? So the fact that I wrote it like this, if I think about the final data flow that is produced, then that's also the case in your real computer. Every single cycle, even though you don't do additions, your processor do additions on garbage data. And then it selects just the useful part. So every single cycle, your machine does an addition, does a shift, does all the things that it could possibly want to do. And then it throws away every one but one. So it's a very wasteful way of computing, but that's the way we have been doing it for quite a long time. Okay? Because physically, the piece of circuit is always there, and you cannot not use it. You feed something to it every single cycle. So all the gates, I mean, you could sort of do power gating or some smart thing like this. But if you don't do this sort of advanced power management techniques, then really semantically, at the circuit level, every single cycle, every single gate of the circuit is active doing something that is then thrown away, okay? So for performance, it doesn't matter that I put this function here or right where it is needed, because fundamentally in both cases, the circuit generated is gonna do every single cycle, everything, okay? Okay. Oops, I don't know what happened. Okay, jumped around. So we just have a few more cases to handle. So we have to handle the case for a control instructions, and then we are done. So we are lucky because it happened to be the case that we have functions that tell us is it a control instructions. And if it's a control instructions of the inst, then we need to just set the data because we are going to feed the data. You are going to understand in a sec why we need to do that. Because in the case of a control instructions, the way we compute next PC is also using a pure combinational logic. And I want to be able to call that functions in all cases because why do I want to do that? I want to do that because at the end of the day, what I want to be able to do is to say PC here is receiving next PC. And I want to be able to compute the next PC here with this function. So let me just do what I want to do, and then I will try to explain. So I want to apply this function, and this function is depending on the instruction. So RV1, RV2, you start and the PC. Okay. But the trick part, yes. There is one instruction which is a jump and link register. Jump and link register is a function you use that you are using when you're doing a call. What's a call? A call is something that, so most of the instructions that I told you so far, they were either touching the PC or producing an output register or touching the memory. There is one that is both changing the PC and a register, and that's the call instruction. Because when you call, you need to jump to where you want to go, but you also need to remember where you want to come back after. So you need to put in a destination register, what is PC plus 4, where you want to come back, and you need to also jump. So if it's a control instructions, even if it's not a jump, you're always going to write this thing, because it's going to be the case that the only case in which you actually write the register is when it's a jump and link. So I'm going to, this is going to become even clearer. And then, so that's good. And then I need to say that the destination is basically the data, right? Because I need to, same trick as before, I just produce the value, which corresponds to whatever I will want to write in the register ultimately. But if I don't store it anywhere, then when I'm going to go to write back, I won't have it. So I need to put it somewhere on my, in my machine, in my microarchitectural state. Okay, and so I think that I'm done with this case. Yes, it does seem like it's correct, except that this is .nextPC. Okay, and I think that I am good. And then we need one more rule. So we have done 3/4, and that's a write-back rule. So this rule is only happening if current state. Also a very bad practice. We are running about a bit less than 100 lines of code without compiling. We are going to run into trouble. Yes? Yes? No, so that's a good remark. It happened to be the case that the exact control 32 functions will return PC plus 4 if it's not a control instructions, and will return the right PC if it's a control instruction. Does it make sense? You know, there is this is actually maybe a design pattern that you're not so familiar with, but you basically want to write little helper function that you can reuse. The question, yes, the question was, does it mean that you always take the branch, that you're always calling exec control 32, and then you always say PC next PC, which is the output of the function? And the answer is that this function exec control 32, its specification conceptually is basically telling you what is the next PC. And the next PC might be PC plus 4 if the instruction you're trying to compute is not control for instruction. Yes?
I've got a question about these pure computations.
Yes.
So we use now these additional helper registers, RV1 and RV2.
Yes.
But it seems like we could compute their values
Yes.
based on the inst, right? Basically doing the computation kind of.
So you are telling me decode is useless. At some level, you're telling me it seems that everything you did in decode, you could have done it directly. Well, there's one thing that you execute did do something which was stateful. The thing it did, it sent something to memory, right? So that we need to do. We need to keep that state. But you are making a good remark, that is, it seems that all the things you needed to be able to compute were basically pure values, and that you could have directly you could have skipped decode, you could have just gone directly from fetch to execute, because the only stateful thing was the instruction, and so you could have kept the instruction into the return queue, and then compute everything, and then push, skip decode, and then just directly read from the memory in execute, and do everything in execute. And that's correct, but it turned out that artificially adding that stage is making it easier to refine the processor later. So right now, you could have done exactly what you suggested, which is to skip decode, to do a 3-step machine, where you do fetch, then you do decode execute in one, and then you do write back in the other. But once you have splitted that thing in 3, it will be in 4, it will be really easy to pipeline it, and to basically add, make it such that you can have multiple in-flight instructions. And that basically will not require to add a new rule at that stage, because the rule will already be there. So, yes?
A follow-up question then, for these pure computations, I guess they're not instantly computed, right? So what happens if you have like dependent pure computations, that somehow the compiler figures out how long their cumulative execution time is to compute the cycle? Or?
Yeah, so the way it works is when you have a combinational function, it's basically a directed acyclic graph. There's a bunch of inputs, and then you have a bunch of operator, which might be like this. There might be some sharing, and then you produce a bunch of maybe one value. And as you're saying, if I have a very long, deep thing, for example, something that goes through 32 different values in a chain thing, certainly that should be slower, for some definition of slower, than some things that have a smaller depth, okay? This is not something that the BlueSpec compiler need to worry about, because this is something that the other tools, which are the downstream tools, worries about. So basically what you output at the RTL level is these functions, and you are responsible as a designer to make sure that this function is not too deep. Because whenever you feed it to the downstream tools, then the tools are going to compute what's the depth of this thing, and it's actually not a logical computation, because this is a very low, when it gets translated down to gates at the technologies that you need to care about, it's not actually just a simple additive property, it's a very, there is interferences and stuff like this, and it does an estimation for what is called the critical path. And when it picks a critical path, maybe it will say the critical path is 2 nanoseconds. That is, statically, I managed to compute that whenever I put any inputs, I always get the output in 2 nanoseconds. And once it computes that, then it sets the clock 1 over this number, and that's the way that you get the speed. So if you write a poor functions where you have a long critical path, then the downstream tool are going to tell you, hey, you can run on 1 megahertz. And then you're like, well, that's kind of bad. And the whole things of computer architecture is basically cutting critical paths up to the moment where it's very small and you can go very fast. Okay? So we just need to finish that thing. So what should we do in write back? Well, so, you know, we have two kinds of stuff. Either it's not a memory instructions, and then the only thing we need to do is to actually update the register inside the register file if it's a destination. And if it is a memory instruction, we need to make sure that we consume the response we get, and then we update the register file. Does it make sense? Okay, so it should be very short. So we want to say if it's a memory instruction, and we need to remember that to be a bit careful, because it should not be an MMIO, because if it's an MMIO, then we don't want to dequeue from the memory, because there is nothing in the memory, and then we would get a deadlock, right? That's actually something important, so let me elaborate again. If I were not to put, so let me write the code and then elaborate on the problem. Oops, sorry. So if I write it's a memory instruction, then I want to get the response from memory. I forgot what the name of memory is. It mem? Mem, okay. Mem.port.a.response.get. Oh no, I'm not in OCaml, okay. Then actually we are always using the same trick in BlueSpec, which is you first define a value and then you overwrite that value in the different case. This way at the end you can use data and corresponds. either coming from memory or coming from previous stage. Okay, and so we have this data, and what we just need to say is that if the instruction is specifying that the destination register is valid, meaning that we need to write to it, then we just write to it. And where do we write? Well, we need to compute the index. The index is also part of the destination of the decoded instructions. It's actually get inst fields the inst.inst.rd. And then we just say, if we remember we don't want to update the register 0, then we can just update the register by writing to the index the data. Okay? And what should we do after that? Yes, I see the gesture. Rinse and repeat. Yes. Yes. Current state. Oh, this was a comment to explain the trick here. Okay. Does that make, yes, question?
Do we need to implement PC, or is that only done during X?
Do we need to implement what?
The
So here, fundamentally, you're asking a good question. Fundamentally, I just did it in execute. I did it early because I know that's an optimization, you could argue, and you might want to put it. Oh, yes, the question is, do you need to update PC, or why are you not updating PC in writeback? You could have updated PC in writeback. But if I wanted to do that, I would have needed to store the computed next PC in some microarchitectural register, and then update the architectural register with the microarchitectural register inside the writeback. And then I realized that actually you never change your opinion about what you should do to next PC inside writeback, so I just lift that one up into execute. Does it make sense? Okay, and then we are hoping that there is less than 1 million bugs in this piece of code. Aha, so there is problems. So it's complaining. It's complaining that I cannot put, this is actually, this is a typical, so students don't like it. So here you should like it because you like functional programming. But students don't like it because there's a lot of type class business in Blue spec, and then they don't understand the error message very often. So what it's saying here is it's saying you're trying to write 0 in the initial decoded instructions field, and it's telling you, you didn't give me a way to interpret the literal 0 as an instruction, so I'm sorry, but I can't compile this. But we don't care because we say this doesn't matter, and then, okay. So then it complains again, and it tells me it's not data, and it's because the name is data in, and then it's not data because there's another one, but it's so big, I can't see more than 3 lines. Data in, where is it? Data in. Tells me response on write is not in that type. Maybe it is not. Why is it not in that type? Because response on write. I mean, you should have caught that mistake. I am busy. And actually, I remember I deliberately added a bug, but okay, so let's remember we added a bug. Because this kind of stuff, you know, you add a bug and then you forget about this. Okay, and then it tells us what's this RV business. I think we named it RD instead of RV, if I remember. Yes, RD. Up. And then what is this RVD business? Well, it's because I need to be a little bit more consistent about my naming. Okay, and then it's telling me that there is no such thing as an address here, and that's okay, there is no such thing as an address because I can recompute it. The address is RV1 plus the immediate, which is get immediate of the inst. So that's a stressful moment. Did something, blah, blah, blah. Okay, so now we run. So I wrote a bunch of tests. So okay, so What is memory? Memory is this thing, which is a big array of 2 to the 16 cell of 32 bits. And how do I initialize it? I initialize it with a file which contains all the bits corresponding to this 2 to the 16 times 2 to the 5 bits. And that thing is basically what's, it's a file named mem.vmh. And it's basically the binaries that I want to load. So there's a whole lot of zeros in that thing. And I need to basically create that file for programs that I care about, okay? So how do I do that? Well, so it's just a little bit of hacking around. So first I need to make sure that I set up, I want to run C. So what should I want to do at the beginning of my program? Well, I want to start by, at PC0, I want to put a bunch of 0 in all my registers, okay? And then I want to set up a stack pointer, and then I want to jump into my main function, okay? And then my main function is going to be a different function depending on what I want to do. So I have a little add test in which I'm going to do a very sophisticated computation. And I have some slightly more sophisticated computation in which I wrote a little matrix. I didn't write. A TA 1 year ago wrote a little matrix multiply function. And it's a self-testing code. And at the end, it's supposed to print something saying that is it okay or is it not okay, depending if the matrix multiply was correct. And I have one final test, which is like probably a hello world of some sort, where it's like just printing the hello world, okay? So when we make, it's just calling the, oh, I can clean. It's just calling the RISC-V compiler, and it's producing a bunch of binaries, and then it's producing a bunch of, a hexadecimal representation of that binary. So let me just show you post-compilation what it looks like. So if I look at the test for add32, at address 0, I will start and I will do all this. Then post-linking, basically, when I will jump and link to this address, it will jump and link to address 1000. And here I have my main function, blah, 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 blah. There is also a function to interact with the outside world. What does it do? Very simple. It's in mmio.c. I actually have, let's not look at getchar because we didn't implement it, but there is putchar. And I have the same address to which I am expecting to do some printing of a character, if I ever call that thing. And then what does it mean to putchar? Well, it's exactly just dereferencing that address and and writing the characters that I want to write. Correct? Yes?
How come you didn't add volatile? You just put the comment saying we add volatile.
Yes, because, so that's a very good question. So the question is, how did you not add volatile? Are you trying to play with fire? And yes, I am trying to play with fire. So actually, if you add, those tests, they are so simple that if you add -02 or -03, the compiler is going to do constant propagation and there is going to be nothing tested. So I only compile with -00, and with -00, this is not going to get optimized away. But this is incorrect, you're right, because in the semantics of C, I should have added a volatile. So what is the difference? So in C, when you have a load or a store to main memory, it can be optimized away or put into a register or do something that it doesn't emit the store to that address or the load to that address. This is perfectly reasonable for memory, because why not, right? There is no problem in hiding the fact that you have done the load or a store. You can just do it in a register instead. But when you are doing MMIO stuff, that's not the same thing, because you know that a load to that address does have an effect, and a store to that address does have an effect. So you need to tell the compiler you cannot optimize that load away. And that's the way you say that is by saying volatile, you cannot optimize that load away. Which is very funny, because I always thought that volatile was a word that means it can volatilize. But no, it's like the opposite. Volatile means that it cannot move. It's very non-volatile. Okay, and so does that make some sense for the test bench of what we are trying to do? And then let's try to make sure that it doesn't work first, and then let's fix the problem. So I need to just copy the dump corresponding in and rename it mem.vmh. So that's what this thing does. Then I run the thing, and then the standard thing of what happened when you do a blue spec program is that. Nothing. It just hangs. So what could be the bug? Okay, so what you do is you go. This is slightly unscheduled, so it's sort of, I thought I could show you a bug dynamically, but I don't know if it was a good idea. So I can start by saying, actually, I would like to trace what is happening. So, and this is really, I want to make you realize how painful it is to debug things. This way you will appreciate verification. So you go there, and then you say, well, I would like to see what is the sequence of stuff that I'm doing. Then you rerun. And then you say, well, I did a bunch of things. And then I got stuck on PC 1004. And then you could basically go and say, well, what's my instructions in PC 1004? So I go there. Ah, interesting. So it did a bunch of things. Oh, wait, it's on the store. So the store is problematic. And then you look at your code. Can someone make a suggestion for why this is all problematic? So stores only happen between execute and write back. So on either a load or a store, I am sending this request to main memory. Okay. And on either a load or a store, I am expecting a response from main memory. But there was this little flag, which has the suspicious name of response on write, which we had set to false, which means that we are sending a message to main memory, that it will not send back a response, but that the rule semantic is that there must be a response for the rule to fire. So what's likely happening is that for the first store of my program ever, I go fetch, decode, execute, then I go to write back, and I'm waiting for the response that will never come, and then I just wait forever. Okay? So maybe if I just do that, it will work slightly better. There is still a small chance that it works, but it could work. Okay? Oops, that's slightly concerning. Thank you. It seems it's doing something. It keeps doing something. Fetch 90. Okay, good. What is 90? Okay, so we come back. I think I know. A dump. It's doing an infinite loop. So it seems that there's something fishy. Everything went right except something. Yes?
Wait, what was the address for halt?
This one. And what was the address that we had specified in our software? It's not FFF, it's FFFF8. Thank you. We could have looked for that bug for a while. Is it gonna work? Yay! Okay, so now we remove that, and we want to make sure that more tests work, right? Because, one program that runs is slightly exciting, but, and I want to show you a program that doesn't work, because it's funny. Okay, so I just want to remove the printing, because otherwise it's just annoying. Okay, so it tells us terminate, so now let's try another test. So I actually have another thing that computes the tumor sword, if you know that. Or if you know it, maybe you're happy, but you don't know it, so you're not happy. And it's actually incorrect for a reason that I'm going to explain in a minute. And then I want to show you matmul, because that's the biggest test. And if it does work, because matmul is self-checking, and at the end it will actually print 0, either O or F, depending on if the matmul worked or not. So it's slightly more interesting. And here it tells me O to say that it indeed took the branch that was mattering. So that's actually a reasonable amount of testing, right? It actually did a bunch of additions. We didn't actually implement multiplication in our case because multiplication is slightly more complicated. You need to take multiple cycles to do it. But we implement multiplication in software. So there's actually quite a lot of instructions that I've run, and control flow has been tested quite a good amount and stuff like this. Okay, so we are happy. We can double check if we wanted, we could try to break it. Like if we do another value here, we say actually, I think this is actually important because very often tests pass for wrong reason. So it's a very good idea to break it deliberately and to add a bug and make sure that the bug is caught in the sense that it should here return that it fails. Okay, and actually I didn't compile the right thing. Okay, and then multi-cycle. And then we have a problem. And why do we have a problem? Because I didn't copy the file. And then it indeed failed. Okay. Okay, good. So this was a little demonstration. Let's just check for one final little test, a little hello world. Hello 32. Oh. Okay. What happens? Guess. It's a cool bug. So I like this kind of bug because students typically, when they run into that thing, they start arguing that, no, it's a problem with my terminal. You know, there's something weird happening, and so I'm like, are you really sure? Like, your terminal is kind of screwed up if it does things like this. Exactly. So what happened is that I told you we are not going to handle load bytes. We only handle load words. And if I look at the hello world compilation, I would see that there is one instruction, which is a load byte somewhere. I think it's a load byte unsigned here. And that instruction is basically necessary because when you do put char, what do? You iterate over all the elements of your array, and you read them one by one, and then you put char them. But what we are doing right now is we are basically discarding the byte alignment information, and we keep reading the full thing. So we keep reading the first character every single 4 character. So now you are very happy to learn that hello, comma, world is actually HHH because there is 4H, and then O because there is 4O, and then the second O because the second row of world is again O, and then bang, bang, okay? So that's a very simple explanation for the bug, or load bytes is basically behaving as a load word, and then we see that kind of behavior. We could easily fix it, it's just that we need to add 5 lines of code, it's tiring, so we don't want to do that. So now I want to briefly go, I think I have 5 more minutes, over what we could do from there. So this machine is terrible. Why is it terrible? Because it always takes forever to execute every single instructions. It always go for 4 cycles. I actually wanted to compile a snacks program because I thought it was a C, but then I thought he would use load bytes, and then I could not compile it. So it's an exercise. But it should be easy because I think it doesn't depend on much. So we can run bare metal C on this machine. So right now, every single instruction basically goes to this little machine, which goes fetch, decode, execute, write back. But, you know, for example, if it's not a memory instructions, we could directly go back to fetch because we already have done everything we needed. So we could do an optimization, short-circuiting there, right? And that would save quite a lot because for every non-memory instruction, which is roughly, you know, maybe 2/3 of the instructions, then we would use only 3/4 of the time that we are currently using, okay? So let's assume we implement this optimization. What is the refinement map, right? What is the weak simulation between that machine, which skip bits, and it's a trick question, and the one that doesn't skip bits? Yes, no, not you. Because you're gonna say the thing and anyone? It's a very easy answer. Yes.
We don't have any value methods.
Exactly. We don't have any value methods. We don't even have action methods. So the refinement map is very easy. It's true. All right? There is no notion of observation here because the only observation is this sort of hacks that I did on the effect of printing, but it's not visible at the semantic level. So I cannot, because of this hack, this question doesn't make sense. So now, I mean, it makes sense, but it's just trivial, and the 2 machines are obviously equivalent, even though we just didn't capture the right notion of observation here. So I would need to do exactly what I said a little bit before, where I would say, actually, every time you do an event, you need to, instead of printing directly, you need to put it on the, as a method that export it on the queue, and then you would basically have your interface of your processor, which would have 2 methods. One that is getChar from proc, and one that is terminated. Right? 2 value methods. And you would also have an action method corresponding to DQ for the ones that getChar. And then you could define, and now what would be the refinement relation? What would be the weak simulation? So this question is not a trick question. Can you think a little bit about it? Yes? Oh no, yes?
I assume they would
What do you mean by equivalent?
They both refine each other.
Yes, that's true, but what would be the relation to show that they are?
Oh.
Uh-huh. And that's, yes? It will be a relation between states, between state of the implementation and state of the specification. But in this case, it will happen that both machines have the same state in terms of state type, but they don't have the same state behavior. So you still need to do something with the relation, right? Like when they are both in fetch, they correspond to each other. When they are both in decode, they correspond to each other. But then weird things happen in execute and write back because sometimes one is short-circuiting and the other one is not short-circuiting, okay? And you cannot really say that the register file map on both sides because the register file will be updated earlier in this machine because it will be updated at execute time, then it will be executed in the machine that we just wrote, right? So we start seeing like the refinement, the phi, the weak simulation will be kind of painful to write. We will need to consider all the cases of saying, okay, what if I have an instruction here and not there, and like start to think about that exhaustively, okay? And we don't want that. So the subject of this afternoon lecture is to not think when you write phi, so weak simulation. Obviously, this is fairly still completely trivial machine. The first thing you want to do is to do pipelining. And pipelining is very easy. Pipelining is just to say, instead of saying that you have fetch, decode, execute that goes into a sequential thing, you just need to say, well, when I fetch, instead of saying I go to decode, I will just push into the queue the fact that I just ask. So you're going to ask your request to memory, and you're going to push a token to say, I just asked something to memory. And then into decode, you're going to say, what did I just ask for? And you're going to pull from main memory. And then you're going to say, well, that instructions, at the same time that I'm going to keep fetching new instructions, I can keep decoding instructions which are other instructions, and I can push them into a queue to execute them, and I can push them into a queue to do write back. And then you can basically do a little train where you have not just one instruction in flight in the machine, but many instructions in flight in the machine. You need to just worry about two things. Is that the question? Yes? It doesn't make it easier to verify the machine, but you want to have a pipeline machine to get good performance. Yeah, sorry. Did I say something that implied that it was easier to verify the pipeline machine? Ah, yeah, sorry. Yes, so I was saying, okay, so little parenthesis. So end of the parenthesis and verification. This would be a pain to write the weak simulation for those two machines. And this afternoon, I'm going to tell you a little bit of how you can generically write simulation relation. And that works very well. End of the parenthesis and verification. Opening parenthesis again on microarchitecture. Microarchitecture, you can do pipelining. It's also a pain to write the simulation relation, by the way, but that's an orthogonal constant. And the technique I'm going to show you this afternoon will also apply to this pipelining technique. Okay, so you will have two things to consider. So basically, it would take me about 15 or 20 minutes to implement the pipeline processor. And the only thing you would do is you would basically take that and then remove the fact that you're in the current stage, because now you don't have a state. And instead of saying that you're saying current state is receiving decode, you would just push into a queue, which you would call fetch to decode queue. And then you would push into a queue, which is called decode to execute, and so on and so forth. And if you want to actually do it, we have a lot of material on that. Just shoot me an email or write on Slack. You have only two things to be concerned. One that is called control hazard. And what does it mean? So if you think about what is the next instruction I should fetch when I just fetched an instruction, you need to guess, right? You don't know yet because you have not yet executed the control flow of that instruction. So you need to speculate. You need to say, well, every instructions, I mean, it's like the weather. What is the weather today? It's basically the same as yesterday. So what's the things that I'm going to do? Well, I'm going to just go to PC+4, and it's very likely that I'm going to get right. So fetch, you are going to say, whenever I'm fetching a place, next cycle, I should fetch to the PC+4. And then you're going to remember that you have made a little assumptions with an epoch. And if you realize later that actually it was not PC+4, then you're just going to flush the pipeline that is behind you because you know that you injected crap in it. Okay? That's very easy. It's like, 4 lines of code on top of what we have. It's a bit tricky because it needs to be well understood architecturally when you can implement it. But once you got it right, it's very easy. And then you have another problem, which is what about read after write hazard and write after write hazard? So if I have two instructions back to back, and one of them is writing to register 1, and the one that follows is reading from register 1. So I have, let's say, an instruction that writes to register 1. I do like register 1 plus register 2 into register 1. And then I have another instructions which read register 1 just after. The problem is that if I am in the pipeline case, it might be the case that I read the register file before it has been updated by the guy that is just in front of me, and hence I get the wrong value. Right? I have back-to-back things, and I know that I only update in write back in the for state. So this was not a problem in the case of the state machine, because I knew I had only one instruction at a time. So by the time I fetched the new instruction, the previous one had completely updated the state. But in the case by pipeline, the previous instruction has not yet finished updating the state. So I need to make sure that if there is someone ahead of me that has a dependency on me, I stall. I just wait until that one has proceeded. So you need just those two little tricks. One thing to notice, is there someone ahead of me that is producing a value that I care about? And in which case I just stall. I do it in my guard. I just say stall until that things happen. And for control hazard, for speculation. Okay, I think that's all for today, for this morning. And this afternoon we are going to do techniques to verify and to write refinement map. Thank you.